Peter Huston, who's going to tell us about algebraic techniques in 3 categories in 2+1D topological order. So the floor is yours.
Thank you. So I'd first like to thank the organizers for inviting me to speak and also to come here and learn from the incredible community assembled here. I should also say that the material in this talk is based mainly on my ongoing joint work with Fiona Burnell from the University of Minnesota. So first, some context. What do I mean when I say topological order? So I think that my knowledge about it can be encapsulated in this triangle here. Anomaly-free n+1D topological phases are, and I was reading Zheng Han's textbook this morning to see, the phases to describe matter when the low-energy effective field theory is given by a fully extended n+1D, I guess I will say framed TQFT. Now, I'm not really a physicist. I'm also not really a TQFT person. I'm actually a fusion category, tensor category theorist. So I'm going to tell you about the tensor representation theory of fusion categories with applications in these areas today.
Are you a mathematician?
I like to say so, hopefully. Now, by the cobordism hypothesis, due to Laurie and others, fully extended n+1D TQFTs are fully determined by their value at a point, which should be a fusion, or I guess multi-fusion n-1 category. This is this bottom arrow here. You can go back, for example, in 2+1D, and from a fusion category construct the TQFT by the Tarayev-Vero-Barrett-Westbury TQFT. You can also go along this arrow of the diagram, and from a fusion category construct a string net model. At least in the case n equals 2, I think that this is pretty understood, which is kind of a physical realization in some sense of state sum invariance that I'll go into a bit more in a moment here as a model of matter in a given n+1D topological phase. Now I should caution that this triangle here is not a commuting diagram because, for example, I am completely ignoring matters such as the chiral central charge, which I think I was warned should be part of the information of a topological phase, but is not completely determined if I just am given the fusion category. So a brief description of what is a fusion category for those who are not so familiar with the definition. A fusion category is a linear category, so spaces of morphisms are vector spaces of some kind, satisfying a long list of axioms. So here are some. It should be finitely semi-simple. So that means that there are finitely many simple objects. A simple object is one whose endomorphisms are my ground field, which is always the complex numbers because I'm that kind of person. And finitely semi-simple means there are finitely many isomorphism classes of those, and every object in my fusion category is a finite direct sum of those. Objects should also be a tensor product. I guess I ought to really have said a linear monoidal category. And every object should have a dual under the tensor product. So if I tensor that object and its dual, I get the tensor unit. Finally, this unit should have been one of the simple objects. So what are some examples of fusion categories with which you are familiar, or at least are accessible if you have not been familiar with the idea before? Well, first I'd like to say the category rep G of complex finite dimensional representations of a finite group G. All these list of axioms is well-known properties. And finitely semi-simple is like Schur lemma and Matschke theorem. Having duals, the dual vector space has an action on it as well. Simple unit, the trivial rep is one-dimensional. Now another example is what I'll call vec G omega. So in this fusion category, there are a bunch of simple objects, and those simple objects form a group, essentially, under tensor product. G is that group. So if I have the simple object that corresponds to G and the simple object that corresponds to H, the tensor product corresponds to GH. Omega here is a co-cycle. When you've gone from an algebra to a monoidal category, one category level higher, a property of algebras, associativity and multiplication, becomes higher data. And that data can take the form of a 3 co-cycle on the group in this case. And one more example of a fusion category that will appear several times in my talk is the Ising fusion category, Experts will say that I should be more specific than this, but I'm going to ignore that for this moment. So this Ising fusion category has three different simple objects, 1, psi, and sigma. And so 1 is the tensor unit. Psi is an object that psi tensor psi is 1. So it is this is kind of like a copy of vec z mod 2 or rep z mod 2. It's an abelian group. Z mod 2 is its own dual, so these are kind of the same inside Ising. And then sigma is another simple object, and the interesting fusion rule there is that sigma tensor sigma is 1 direct sum psi. Now, if you know anything about dimension of vector spaces, when you direct sum the vector spaces, the dimension adds up. When you tensor, it multiplies. So we solve for polynomial equations and also assume that 1 is one-dimensional. And we could find out that the dimension of psi was 1, and so the dimension of sigma was square root of 2. So this is not just some vector space with its vector space dimension. Something subtler is going on, which I will hardly mention. Also, maybe it's worth mentioning very briefly that the higher associativity data for this Ising is interesting. But I guess I later realized that I don't actually need that, so I'm going to skim over it. So, string-net models. So this is, again, a way to take as input a fusion category and as output a somewhat physical system in a given, or in a certain topological phase. So I think the earlier example of this is Tor code, which has already been mentioned in some talks today, but I will speak about it again a little. So this is highly related to the group Z mod 2, and I'll call the non-trivial element of this group G, little g, and the trivial element 1. So what we do is we have a square grid, at least locally a square grid. Globally, there could be some interesting manifold, like a torus, that this grid tiles. I'll not be specific about that right yet. And to every edge of this grid, where I put these blue dots, I'm going to assign a Hilbert space. And it's going to be a two-dimensional Hilbert space in this case. Or maybe you should say a Hilbert space of functions on the group Z mod 2. And then the overall Hilbert space that I get from my whole lattice is just the tensor product of all these local Hilbert spaces. Now, on that Hilbert space, I can define an operator which I'll declare to be the Hamiltonian. And the way I define it is like this. It will be minus the sum over every vertex in my Hilbert space, the tensor product of Pauli Z on the 4 surrounding edges, and then the identity operator on every other edge I didn't draw in this little picture here. And then for every face, which is a letter which is denoted by P for plaquette, I will have, for the edges around that, Pauli X. And these terms are called AV associated to this vertex V and BP associated to this vertex P. So this is all kind of highly built out of the fusion category vec Z mod 2. Or if you like, and you want to think in terms more familiar from Catherine's talk, just the group Z mod 2 really. X is like the operator that multiplies by G, if we view our basis states in 1 and G, and Z is an operator that is like the representation, the non-trivial representation of Z mod 2. I guess I could have made a non-trivial choice of associativity data here to get what's called semyon, and I'm not doing that. So what is the ground states for this Hamiltonian operator? So if I have, if I just would take the sum of these vertex terms and not include these plaquette terms yet, because the eigenvalues of Z are 1 and -1, and I've got this minus sign here, I want to have at every vertex an even number of edges in the state labeled by G. So I want to have pictures like this that are essentially a loop gas made it out of a collection of loops across this lattice here. And then if I apply BP on the plaquette P, that switches whether every edge around P is on or off. So it would go from this configuration to this configuration. So in the ground state of BP, the two configurations exchanged by PP have to be the same amplitude. And so what this overall means is that I can locally homotope my loops, create and destroy them, and if I can get from one configuration to the other, then in the ground state, those two have to be in the same amplitude. So the overall picture is that the ground states of H on some, this Hamiltonian, if I put my grid on some manifold, and make sure that like each cell is locally contractible to avoid weirdness perhaps, is the Z mod 2 graded cohomology of the manifold. Or it comes from the Z mod 2 graded cohomology. Essentially asking how many blue loops go all the way around each non-trivial loop in the fundamental group. And this Hamiltonian is what's known as a frustration-free commuting projector Hamiltonian. Commuting projector, all these operators that I summed up are commuting. They're not projectors, but their spectrum is 2 points, so I can rescale them. Frustration-free is that there is a simultaneous lowest energy eigenstate for all of these terms, right? So a priori, that would not have to exist. Maybe the lowest energy eigenstate would have some of these terms not in the lowest state because the vector space that was simultaneously the lowest energy eigenstates for all these commuting operators could be just a zero vector space, but that doesn't happen. So into our code, we have these excitations, which I believe were mentioned, for example, in Poshen's talk. Type E excitation. This is what happens if I apply poly X along a string in the lattice. And since X does not commute with Z, and I have this AV term made out of Z's, at the ends of these strings, where I've only applied X to an odd number of edges at that vertex, I will move from the lowest energy eigenspace of that AV term to a higher energy eigenspace. So I can locally detect that, hey, something has changed, there's an excitation, and it's right here. If I look anywhere else along the string, I've applied X to two mod 2 edges, and so I did not excite those terms. And because poly X and poly Z and the lattice and dual lattice, everything is completely dual, AV and BP, I can also pick a path in the dual lattice and apply poly Z's along all the edges that it crosses and get what's called M excitations. And then there's also an excitation of type I'll call epsilon, which is a fermion, which is just doing E and M in parallel. Why is this a fermion? Well, if I look at the ground state and I apply a string of poly Z's like this, and then a string of poly X's like this, and then apply another string of poly X's to close this up to a loop, and another string of poly Z's, get these two squares, they cross at two different places. And so whether I get a 1 or a -1 depends on the order in which I applied all these operators. And if I go in this particular configuration, I end up multiplying my ground state by a -1 scalar. So this is the interesting braiding of anions, at least in the case of Tor code. And let me remark briefly what a more general string net model looks like. So I replace my fusion category of XZ mod 2 with some other fusion category, rep G, easing, something more exotic and fun. Now I'll have my grid be a hexagonal grid because this is easier to state when I have trivalent vertices. And I'll define it in this way. I have Hilbert spaces on edges and vertices now. On the edges, the Hilbert spaces will be labeled by the simple, will be the Hilbert space spanned by the set of simple objects, a set of isomorphism classes of simple objects in my fusion category. And on the trivalent vertex Hilbert spaces, there will be the direct sum over all simple objects x, y, and z of hom in my fusion category from x to y, z. So if my fusion category is rep G, you could think of these as being the representation intertwiners from a simple, from an irrep to the tensor product of two irreps. And then I have AV and BP terms, which I'll describe conceptually. So conceptually, the AV term checks that the state, the labels on each of these edges and vertices type check, so that I've got a state which is a linear combination of diagrams in the graphical calculus of rep G. If I take a contractible region and like read off the labels in it, I can see some complicated intertwiner from some big tensor product of irreps, if this was rep G, to some other big tensor product of irreps that is well typed. And the BP is a sum with certain normalization of inserting loops of all the simple objects. And so what that would conceptually do is make it so that if I had two big maps from some product of intertwiners to some product of irreps to some other product of irreps, that when you composed all these trivalent maps, gave you the same intertwiner in the end of the day, they would have the same amplitude in the ground state. And so this is really getting to the
so in general, I just need like a ribbon graph on my surface. Like if I have a general surface and then like a general cell decomposition, or it needs to always be like a regular graph like this.
It does not need to be a regular graph like this. If I want to have a graph with vertex of higher valence, for example, then I would just need to include more simple objects when I define the HV for that vertex. But that introduces some practical complications when working with these models, so people often prefer to work with vertices of the smallest possible valence. Thank you.
Question here. Are there analogs of operators that create and push anyons like there are in the toric code?
Absolutely, there are, and I didn't want to get into it too heavily, but there sure are, and maybe I'll get into it by another angle than literally telling you what the analogs are. In fact, very shortly. Of course, great question, but yes, there totally are. So the theme of this conference was something defects, and I work with defects, so I thought it was a fun conference to apply to. So let me tell you about the topological defects in Tor code. So far I've basically told you how to build like a 2D bulk system. But I can, of course, have some codimension 1 defects between one such system associated to one fusion category and then a system associated to some other fusion category. Examples are the defects mentioned, I believe, already by, for example, Poshen in his earlier talk, right? Of the smooth and rough boundaries on toric code. So I could have my lattice continues in this direction, this direction, this direction, and then here it just kind of stops at this edge. This is called a smooth boundary, and over here I don't have anything. Or a rough boundary where it's very similar, but I truncate it in this way, where just I have edges sticking out. I'm going to say that this is like a smooth boundary, except that on the boundary, instead of 2-dimensional Hilbert spaces, I put 1-dimensional local Hilbert spaces, which of course when I tensor product all the local Hilbert spaces, you cannot really see. And I'm going to allege that these also have a categorical structure. The bulk was described by fusion categories. These boundaries are described by bi-module categories between fusion categories. And if I don't define that, maybe you'll forgive me. If you know what bi-modules between algebras are, categorify that definition.
So are the boundaries really bi-module categories or module categories? Like there's the other fusion category.
Well, that's a good question, right? So for this example, I would say that the bi-module category is vec z mod 2 as a vec z mod 2 vec bi-module. So you may well say, well, that's just a module, and you're right. But like if I would put a non-trivial thing on both sides, then it would really be a bi-module. And of course, in the language of Catherine's talk, you may prefer to just think of this as z mod 2 as a set with a z mod 2 action on the left and vec on the right, and I'll just kind of linearize things later on, and that's also a great way to think about it. Now, this is like vec as a vec z mod 2 module. And then there's this weirder boundary, which you may have seen. I first saw it in this paper of Kataev and Kong, which I'll reference many times in this talk actually, of a codimension 1 defect between Tor code and itself, where I kind of mess up the lattice and break it like this. And then what do I do with the Hamiltonian here? BP terms, at one of these boundary boxes becomes this operator. And the BP terms on the other side and the AV terms are kind of modified in a similar manner, which I will not write out. I allege that this is described by vec as a vec z mod 2 bi-module, which seems very boring, but I have some interesting data for the fact that a bi-module, right, the fact that a bi-module, the left and right actions commute and that the bi-module actions are associative is instead of being a property, it is also now extra structure that I'm up one categorical dimension. And this allows me to put in some kind of cohomological data. And so, which is how Catherine said it in her talk. And so that's how I'm kind of getting this. Working out that this is correct is an enlightening exercise, I think.
Sorry, this is in what sense?
Sorry, go ahead.
Go ahead.
So in what sense are you say you write topological defects? Is this just as a word, or does it have some precise meaning in here?
Well, I would say that
Topological.
perhaps the meaning is that these are gapped boundaries. But to tell you what that means, I'd have to tell you that the original Hamiltonian is gapped and what that means, which would perhaps take us a bit far afield. But yes, there is a precise meaning.
What is it?
the right way to say it in this context?
I think you already said it. Gap is topological. That's pretty much what it is. So this is the way to extend Hamiltonian from the both gap all the way to the long run. The generic about this gap is.
Thank you. So
you're letting me put some surface in space, not linear, just a line in space in this lattice where you have some kind of defect, I guess.
yeah, so that's like this dashed orange line.
Is this supposed to be the vertical surface that exchanges the end?
Yes, that's what this is. This defect is the EM swap.
So is there a way on the lattice to sort of canonically count the number of ways in which this sort of line ends? So I mean, we know, right, in the category here, there should be two boundary conditions for the surface. Can you count this on the lattice?
Can I count this on the lattice? So I think there may be some different ways I can interpret your question, but one of them is that this is the subject of the talk.
Okay.
So
you're going to deduce two.
yeah, I'm definitely going to deduce that, for example, from what I'm going to show you. So perhaps you'll be satisfied, and if you're not satisfied the next time I come to this example, then re-ask again, absolutely.
I mean, well, yeah, my satisfaction, I guess, would depend on whether you phrase this at the level of the lattice or not. If you appeal to, like, continuum filters and have enough.
Oh, I'm not going to appeal to a continuum thing, that's for sure. It is at the level of the lattice, but maybe as I joked to Liang earlier, this talk is lattice models without lattice models, so maybe you won't like it, maybe you will. We'll see. There's definitely going to be an explanation, and I'm very curious to see whether you like it or not. So, indeed, this, because of the way that like z and x were swapped on different sides of this defect, this is kind of the defect where I could, that swaps the E and M anyons. I could have a string going across it that creates an E anion on the left and an M anion on the right. And I could also have this defect stop at a codimension 2 defect. You know, below it I have this weird break in the lattice. Above it I have no break and everything is normal. And so this is a codimension 2 defect between codimension 1 defects. Now one of them is the trivial defect. As a mathematician, I still call it a defect. And this is the appropriate data for this, I assert, is a bimodule functor, which is like the categorified version of a bimodule intertwining map. Let's not get into what that is either. So the interesting thing is that if I can bring E around and create M, so I can bring E around, create M, I can bring that back around, create E, I can make a closed loop. This is like bringing a fermion all the way around the defect. And so the fact that I can do this will have interesting consequences later. Remember that. Now, so what about the topological excitations E, M, and epsilon? You know, where did they come from? The input fusion category is vec z mod 2. There's more than z mod 2 here. There's like z mod 2 cross z mod 2 in some kind of way. So I'm going to say that, well, excitations, really, they are just codimension 2 defects between certain codimension 1 defects. The trivial ones where I didn't modify my Hamiltonian at all and there's no defect, which is given by z mod 2 as a z mod 2 bimodule. Now, if you know anything about rings and modules, you may know that if X is a ring, then X is an XX bimodule with just multiplication giving the action, and the XX bimodule intertwiners from X to X are precisely in correspondence, canonical bijection, with the elements of the center of X. So this endomorphisms of the identity bimodule is a good higher categorical definition of center of any kind of monoidal gadget. So these excitations are what's often called the Drinfeld center of X, but I've got it into I've got in that direction in an algebras and bimodules way. So previously I just had this triangle, you know, TQFT, fusion categories, and so on, which didn't mention about defects. Let's update the triangle to reflect about defects. So n+1d topological defects, phases with defects, which includes just the bulk phase where I didn't have any defects that I count as trivial defects, should correspond to things where the low energy effective field theory, and now I'm worried that Jing Hong will tell me I'm not quite right, but is the n+1d defect TQFT together with a particular selection of stratified manifold to evaluate on and defect data choices for the strata. And under a defect cobordism hypothesis, this should correspond to what I am loosely calling, for the purpose of this talk only, n+1 categories of topological order. So what is the 3 category of 2+1d anomaly-free topological orders for our purposes here. In other words, what is the input data that I would need to do this lattice model construction and specify how to build defects of every codimension? It is the category, the Morita higher category, the category of fusion categories and bimodules, which I'm calling FuseCat. So objects in here are multi-fusion 1 categories, and I just kind of sketched for you how I can build from one of those guys a StringNet 2D bulk lattice model, codimension 0 thing. Don't worry about multi. 1 morphisms are bimodule categories, which tell me how to build these codimension 1 defects or domain walls that we just saw examples of. 2 morphisms, bimodule functors, which tell me how to build those 0D junctions. And 3 morphisms are bimodule natural transformations, which tell me what the local operators commuting with the Hamiltonian in a local area in one of these defect networks will be. Now, one thing I should mention is that everything that I've just said and everything that I will say henceforth in this talk completely lifts, almost effortlessly in fact, to the case of anomalous, by which I mean all but once extended, which in this case means twice extended instead of fully extended, TQFTs. So twice extended 2 plus 1D TQFT should correspond to 2 plus 1D boundaries for invertible 3 plus 1D TQFTs. And the invertible 3 plus 1D TQFTs by the cobordism hypothesis correspond to fusion 2 categories with trivial center, which are just the suspensions of modular tensor categories. I know I'm just saying a bunch of random words for some people, but this is just a sketch for those who know. And so they're given by modular tensor categories up to Witt equivalence. Cite for this some works of Kong and Zhang, Theo Johnson-Freid, and many others. And so we can modify this story of the 3 category fusion categories to get an anomalous picture. An A-enriched fusion category is a fusion category X together with a functor from the modular tensor category A, whatever that is, into the center of X, the category of excitations we just saw. And then we adapt the definitions of bimodule functor, and so on, just to have some nice natural compatibility conditions with these maps from A to the center.
This means like enriched in the typical like category theory sense?
Yes, so this doesn't look like enriched in the typical category theory sense, but with some tensor category knowledge, you can transform this into that if you so please. Good question. And in StringNet model constructions, this corresponds to taking a certain 3D StringNet model associated to the modular tensor category A called Walker-Wong models, which models the invertible 3 plus 1D bulk TQFT, and sewing one of these StringNets I've just been showing you onto the boundary. I believe some examples of this were given in Walker-Wong's original paper, and some of the theory and details were further developed in my joint work with Green, Kawagoa, Pennies, Prudell, and Sanford last year. And that whole table, I just like stick a bunch of A's everywhere and say on boundary of Walker-Wong on the right side, and everything that I tell you about anomaly-free StringNet models works perfectly for the anomalous ones for the whole rest of the talk. So if you're somebody who cares about such things, that's nice, I guess. So algebraic techniques. I'm supposed to tell you about algebraic techniques in this category of fusion categories. So I want to tell you strategies for doing particular computations you want to do in these 3 category of A-enriched fusion categories. Like, what are all the 1 morphisms between certain 0 morphisms? What are the 2 morphisms between certain 1 morphisms? What are all the compositions, etc., etc.? Just computations that don't rely on choices of representatives. So fusion categories determine the 2 plus 1D bulk theory, but what we kind of just saw above tells us that Morita equivalence is the appropriate equivalence notion of fusion categories, where Morita equivalent fusion categories determine the same bulk theory. Indeed, I said all this stuff about centers. Well, the center is a Morita invariant. If you know about rings, you know this is true. I'm just telling you it's also true for fusion categories. So I want to tell you computations that don't rely on making a particular choice of representative of fusion category X in the Morita class, or in this A-enriched setting of a particular modular tensor category A in a given Witt class, and also techniques which enjoy a natural interpretation in the lattice models because they are based around string operators, like the operators creating E and M excitations that we saw above. So I'm just going to kind of tell you philosophy of how to do all that, completely choice-free, going from bottom to top in this 3 category. So first of all, zeromorphisms. If the zeromorphisms, the things that parameterize codimension 0 defects, i.e. the bulk theories, are fusion categories up to Morita equivalence, what's my Morita invariant replacement for that? It is just the center that I mentioned to you previously. It's the theorem that the center is a complete Morita invariant of A-enriched fusion categories. The unenriched version, I believe, is due to Muger. And the A-enriched version, I think, more or less falls out of works of Davidov, Muger, Nikschik, and Ostrich. So then, in other words, the anion theory, the theory that tells you what all these excitations are that you can move around, is already a Morita invariant thing. One-morphisms. Instead of looking at bimodules between fusion categories, I can look at Witt equivalences between modular tensor categories. So what is a Witt equivalence? So if I have a bimodule category M between fusion categories X and Y, I can look at the XY bimodule functors of M, and that is a bimodule category between the center of X and the center of Y, and it is also a fusion category in its own right. You should think of these things as being excitations that can move topologically, sliding up and down, but only on the wall. And these things are the topological excitations that move around in the bulk. And if I take something in the bulk from the left or from the right, I can smash it into the wall and see what it is as a wall excitation. That gives me an action. And so this is a fusion category, which is a bimodule for these modular tensor categories. And when I say it's a Witt equivalence, I just mean that the center of this fusion category is the Delian product, essentially just like a higher version of tensor product of these 2 modular tensor categories. The center functor is fully faithful. This is, I think, the title of a paper by Kong and Zhang, and the details of transporting that and some of the related results that are needed to make what I'm going to say later effective, I did in some joint work with Burnell, Jones, and Pennies. Now, so far so good. The problem is that the enriched center functor, or even just the regular old center functor, is not even a functor if I try to extend it beyond 0 and 1 morphisms. So when I said that the enriched center functor is fully faithful, I mean that, well, I have the 0 and 1 morphisms that are fusion categories and bimodule categories up to higher equivalence. The category with the 0 and 1 morphisms are modular tensor categories and Witt equivalences up to higher equivalence. I have a functor between those 2 things, which is fully faithful. But if I try to extend to 2 morphisms, bimodule functors and whatever 2 morphisms go between Witt equivalences, I actually don't even get a functor. And the simple example of this is that if I just make my enriching thing A and my fusion categories X and Y vec, and I make my bimodule category the n-fold direct sum of vec, so just a linear category with n simple objects, no higher tensor product structure or anything, well, the center of M, which means the vec-vec bimodule endofunctors of the n-fold direct sum of vec, is the n by n matrices over vec. This is just categorifying the fact that if I have an n-dimensional vector space, its endomorphisms is the n by n matrices over the ground field. So this thing is highly decomposable. I can project onto all the sum n's, but I think many people well know that there are no non-trivial ideals in the algebra of n by n matrices. So this thing is not decomposable. And so a map like this cannot, that would send this to this cannot be a functor. So we're going to have to be a little smarter if we want to, in a similar way, just talk about the topological excitations and wall excitations and somehow understand point defects. Like, just as a quick reminder, the point where this weird break in the lattice ended. But to talk about point defects, I'm going to first have to say a little bit more about how you work with one morphisms, because it's going to be necessary to understand the 2 morphisms. So given a bimodule M from X to Y in FuseCat, I can actually associate to that two objects in the centers of x and the center of y. Because what I can do is I can just take this bimodule and close it up into a circle. And then if I zoom out, this is just one small area within a y bulk lattice model where something is different. So this must be equivalent to an enneon or a direct sum of different enneons. And I can also close it up the other way and get an object in the center of x. And these things are actually going to be commutative separable étale algebras, or what I will call for the rest of this talk condensable algebras in the center of x. Let me just sketch for you very briefly why this is an algebra. The point is that here I'm kind of drawing what you would see in the lattice model. This is a 2D picture, but really I should be drawing in a 3 category. I've not created space to draw operators. So if I have one copy of this algebra here, and one copy of this algebra here, it's well known to those who think about TQFT, there's a pair of Pants borders that makes things into an algebra. And so the proof that this is a commutative algebra is basically the same proof that a 1 plus 1D TQFT is Frobenius algebra.
Why is it separable?
Why is it separable? Because I baked a lot of separability into things by saying I was starting with fusion categories.
But this particular algebra. So it's a tile algebra, so it's in particular separable, right? So bubble move should hold.
That's true.
Does it?
If you normalize things right, and your definition of separable cares about normalization, then yes. And again, I will just reassert that it is because I baked a lot of things into my definition of fusion category that make this so, some of which I skimmed over. That makes separability almost automatic. It's a good question. And all Witt equivalences are of a canonical form. They are completely determined by this algebra of, I guess, kind of tracing to the left, algebra of tracing to the right, and a braided monoidal equivalence between the enneon theories you get if you take local modules, whatever that is, over these algebras. And there are a lot of technical details that I don't want to get into so heavily, but I do think that this diagram is interesting. So if I'm given 2 bimodules, and I want to know what happens when I compose them, so I've stacked 2 domain walls side by side, I can just zoom out and view this as one domain wall between the theory on the far left, theory on the far right. That may be decomposable now. It may be the direct sum of several different gap domain walls in general. And so how do I compute what those summands are? Well, so let me draw a diagram in the 3 category of fusion categories. If I have a couple of codimension 1 sheets associated to the bimodules, you should think of this as down here is the line in the lattice model where the bimodule, where the domain wall lives. Here's where the domain wall lives. And then the sheets are extending upwards in time. These are world sheets. And I have an operator that can act locally on the ground state here. I can deform this picture because I'm working in a fully dualizable higher tensor category, since I've Douglas, Schomer, Priest, Snyder, to this picture. And so what I'm actually getting is a map between, well, this is like the world tube of one of these algebras. This is the world tube of another of these algebras. And so the algebra that decomposes of local operators, which decomposes a pair of domain walls into its indecomposable summands, is just the algebra of local operators from one of these algebra objects to another. The product on this thing is kind of a convolution product. I call it like this. So if I have 2 maps from R to L here, then I can do them in parallel, get a map from R tensor R to L tensor L. I can multiply the 2 copies of L, and I can co-multiply, which is something I can do because of separability, the 2 copies of R. And so if R and L will be the same, this is kind of like a quantum Fourier transform or realization on your condensable algebra.
Do you do general, let's say, necessary and sufficient condition trivial domain wall compared to the
So a sufficient condition is that L and R are the same. Or maybe that all the 4 algebras in the 2 domain walls are the same. And you see some examples of this form very, very shortly. I don't think that's necessary though, because I could make things more complicated and still have it canceled. So we just saw a lot of abstract theory. Let's get back to the Tor code, which maybe we understood, right? Like, okay. So if I can, so earlier we saw that we have this interesting Ising fusion category, which included Vex Z mod 2 as a subcategory. And I'm just kind of giving you some reminders of the details of Ising. So one thing that I could do with that is I could have a lattice model where on the left I have the Tor code that I showed you earlier. On the right also Tor code. In the middle a strip of the Ising theory. And on these walls between Ising and Tor code I can again put Ising. And if I were to answer the question of like what happens when I wrap up these walls, so the center of Ising is actually itself has a modular braiding, and so I can describe that as a tensor product of two copies of Ising, one which has a reverse braiding from the other, but if you're not familiar with braidings, don't worry about that part. And the algebra that condenses is the tensor unit together with the object given by essentially a psi in each of these copies. And this is essentially a copy of rep Z mod, the regular algebra of Z mod 2 inside rep Z mod 2 inside the center of Ising. And so using these techniques, we can see that this stack of domain walls, where you have this Ising sandwiched between regions of Tor code, decomposes as two domain walls from Tor code to Tor code. One of them is the trivial domain wall. And so this is an example of exactly what I was just saying. I condensed the same algebra here and here, and I got the trivial domain wall here. And another is the EM swap boundary, where like the lattice was all offset by half a unit that we saw earlier.
Generally, in a trivial domain wall, anytime you do a condensation, just do a one more
Yeah, that's right. If all I'm doing is I have one condensable algebra and I just condense it over here and not in the middle, you always get a trivial domain wall. And the reason for that is because the category of local A modules is a summand of the category of AA bimodules, where A is your algebra. So, and let me make this even more concrete in terms of anyons. Like, what are the operators that span from this domain wall to this domain wall in the lattice model sense? I can make a string operator that brings an enyon from the left domain wall to the right domain wall. And if it's one of the enyons that could vanish on that domain wall, like we learned in Huston's talk, E can vanish on the rough domain wall, M on the smooth. So in this case, if it's psi bar, this is a non-trivial operator that preserves the space of ground states. Now psi bar braids non-trivially with the enyon sigma tensor 1, or I could have also said 1 tensor sigma from the Ising theory. And if I had, let's say, my enyon trapped between the domain wall and there's a string coming out of it, maybe the other enyon is very far away below, then this actually becomes a point defect. A point defect just like the one we saw earlier, where the orange domain wall switches to the trivial, or the trivial switches to the orange. So this domain wall we saw here could actually be realized by a thin strip of Ising theory with an enyon trapped in the strip. And all point defects between summands of composite domain walls arise in this way, by trapping enyons in the middle strip. This is not so hard mathematically. It's a proposition I proved in joint work with Bernal, Pennies, and Jones. Although maybe it's been known earlier, especially in the unenriched case, I'm not sure. I should also mention that if you really want to look into the lattice model details of this Z mod 2 Ising relationship, there's a great paper by Heinrich, Bernal, Fitkovsky, and Levin, which Louisa will probably mention later perhaps, which details this in some great detail, I think.
So about the previous slide, you can repeat this for any Tambara Yamagami category instead of Ising.
Yes, that's true. This is related to the fact
decomposes like on the right hand side.
Maybe what that thing on the right is can change, obviously, but this is roughly correct because the point is that Ising was a Z mod 2 extension of Vex Z mod 2. So if ever I have a group extension, then I can have a condensable algebra associated with the regular representation of that group. Here the group is Z mod 2. And so I get a similar story. Absolutely.
So
one Frobenius indicator, what happened for the Tanzania-Yamagami, for the Ising category.
Sorry, say that again?
So if you take the Ising category with the other Frobenius indicator,
Well, so then,
the point like operator in the point one.
so that will also change what Ising bar here means. So I think that even if you take one of these like conjugates of Ising, you get a similar story no matter which one you took, which is why I thought I was okay to be vague earlier. I believe it should be similar because all that matters is that I have a Z mod 2 extension of Vec Z mod 2. And I think that even if I change the Frobenius Schur indicator, isn't it still true that 1 plus psi is a copy of Vec Z mod 2 with the trivial associator? But if you change it to the associator of Simeon, which I don't think is possible, then something different would happen. So I do want to mention, but I did promise you that I was going to tell you not just about, the bulk and codimension 1, but actually tell you how to deal with codimension 2 things. So I have to do that. And the point is that if you are very clever about using your knowledge of codimension 1 things, you can actually also classify codimension 2 things and work out their fusion rules just by working on the Ennion theory and never having to pick representatives in the fusion category, which I thought was nice. So here's how that kind of goes. Suppose I have 2 fusion categories X and Y, and I build these bulk models, and then I have 2 bi-modules here, and I want to have a codimension 2 defect that lives at the junction between these 2 domain walls. I'm going to use what's called the folding trick, or dualizability of objects in FuseCat, and say that, well, I could actually just fold this over and consider this as a domain wall between a stacked X and Y monoidal reverse theory and Vec on the right. I'm really just bending my sheet. And so this would correspond to, on the left I have X tensor Y monoidal reverse, and M and N are bimodules to Vec. And then I could actually do another folding trick and fold it like this. And get this tube, get this like cup picture here, where the defect lives at this point. So now what I have is a bimodule category from Vec on the left to Vec on the right. At the bottom here, I have the trivial bimodule from Vec to Vec, which is just Vec, very, very boring stuff. And then this other bimodule is M monoidal reverse relative tensor product over X tensor Y reverse with N. And when I say monoidal reverse, that's of course the wrong thing to say. It means move the action to the other side. And so over here, XY bimodule functors from M to N are Vec-Vec bimodule functors, or just linear functors with no additional structure, from Vec to this complicated category here. But linear maps from a one-dimensional vector space to some other vector space are just like vectors in the target. You just ask where 1 in the complex numbers went. And it is similar one dimension up. Linear functors from Vec to some complicated linear category are just the same as objects in that linear category. So this category of functors is just the same as the target category. And since it is just a linear category, it is the direct sum of n many copies of Vec, one for each simple object in this linear category. Just like a vector space is the direct sum of finitely many one-dimensional vector spaces if it's finite dimensional. So what that means is that to know what all the possible things I can put at this point are, I just need to know what are all the possible sectors, what are the possible summands of the composite domain wall where I compose this domain wall with nothing on the left, this folded theory in the middle, and this domain wall on the right. And so I can use my knowledge of composition of one morphisms to tell me all about two morphisms. So that means that the xy bimodule functors from M to N are representations of this algebra, the space of maps in the center of this folded theory, x tensor y bar, from 1 to what I'm going to call L of M, L of N, which mean the Lagrangian algebras, the algebras that condense when you go from this stacked theory to the vacuum at this wall. And the interpretation of that in terms of string operators is, Well, if I had a string operator that goes from this wall to this wall and produces no excitation, that's basically a string that's wrapping around this little tube. And if I unfold like this, that's basically goes around the top and then around the bottom. And if I unfold more, that's just a string going all the way around this vertex. And so it turns out that the algebra of string operators that go all the way around this vertex, ways to take an anion in your lattice model, tunnel it through this domain wall as some other anion, and then tunnel it back as the first anion and make a closed loop. Representations of that algebra of string operators correspond to the possible ways to put a bimodule function between these fusion categories or a junction at this vertex. And since we can compute what the summands are, I guess I didn't tell you the details of how you actually compute which bimodule category each summand was, but I promise you can compute it using the same techniques I sketched earlier. You can actually manage to figure out what this circle algebra is without ever, just from knowing the modular tensor categories in the bulk, the weight equivalence of the boundary, without ever picking a fusion category at any time. Now, for those who know that modular tensor categories like non-degeneracy, how this is often invoked in lattice models, if I have an anion sitting here, I can braid all the other anions around it, I get different phases for each one, I can thereby detect what anion I braided around. I'm just telling you, this also works for all the codimension 2 topological defects in a certain way. And we can also compute the vertical and horizontal compositions of two morphisms. If I had two topological defects, one from M to P domain wall, and one from P to N domain wall, well, I have these algebras encircling the top defect, the bottom defect, and encircling the whole system. And then there's also an algebra of local operators that consists of kind of all the things you can do here, preserving the ground state, but now there's a trivalent junction. This algebra can be shown to be Hom in the center of X tensor Y from 1 to the product of all three of these Lagrangian algebras, which, by the way, is not necessarily a commutative algebra anymore. And so by seeing how these orange algebras, like the one we saw before, act on the green algebra, we can compute the vertical and horizontal compositions of two morphisms. Given the full details, it's kind of involved, but I'll illustrate with an example. So if I had, so remember this defect here, this codimension 2 defect where our weird break in the toric code lattice ended. Well, what if I had a line of break in the toric code lattice terminated by two of these defects? We saw earlier that the only interesting string operator you could do around one of these defects is to bring in a fermion all the way around. So I can bring a fermion around the top one, I might get a 1 or -1 phase. I can bring it around the bottom one, I might get a 1 or -1 phase. I could bring it around the whole pair of the defects, and I might get a 1 or -1 phase. And the phase at the top and the phase at the bottom, the product of those phases will tell you the phase when you go all the way around. And so the consequence of this is that when you fuse these two topological defects to get just a combination of anions, right? Because if I look outside this local region, I just have undisturbed toric code bulk theory. I'm going to get a direct sum of two possibilities. Either 1 plus the fermion, which are the two options that would have made this phase a plus sign, or E plus M, which are the two options that would have made this phase a minus sign, which recovers the fact that you mentioned earlier that there are two different possible species of topological point defect here.
I completely agree with what you're saying. I agree with your argument. It's just that probably it's not fair to ask. This isn't shown on the lattice, right? I'm just wondering if you can explain on the lattice. But maybe it's the wrong topic to be asking this question. I agree with your categorical result. I don't think it's on the lattice.
Well, I guess what is shown on the lattice, or what can be shown on the lattice, if I would elaborate a bit more, is that if we agree to say that this is either 1 epsilon E or M based on braiding toric code anions around the whole pair, then we can actually check these phases with string operators on the lattice, and then it will clearly be true. And maybe I could justify more why this story really does work out in the lattice model, perhaps later on. I'd certainly be interested to discuss it. So let me conclude by remarking how this compares to what you would have found in the 2012 paper of Kataev and Kong, which addressed many of these similar topics, the codimension 1 defect, codimension 2 defect, and so on. So there, the bimodule functors from M to N, which were the codimension 2 defects, were given as the representations of what I like to call a generalized tube algebra, the tube of M to N, which is basically diagrams in the bimodule and fusion categories that live on a tube like this, describing local things I could insert in the string net right near the site of the defect. And these algebras were given these algebras were shown to have a C-star Hopf algebra structure, or I would say that they collectively have a C-star Hopf algebraic structure. In other words, this system of C-star Hopf algebras was basically telling you how to understand the entire two category of morphisms in FuseCat from X to Y. And the details of that are kind of complicated, but they again involve some, very lovable pair of pants type pictures that I've written down here for no real reason, since I can't have time to talk about them. So how does our story compare to that? Well, we also have something very similar. I have, this green bimodule in place of a co-multiplication. Our algebras are smaller than the tube algebra. They're all abelian. If my results are correct, then they must perforce be the centers of the tube algebras considered in the paper of Kataev and Kong. So I think those are all pros. Makes it easier to compute when you have a smaller algebra and the algebra is commutative. The con is that our system of algebras is not a C-star Hopf algebras, but C-star Hopf-ish algebras. A Hopf-ish algebra is like a Hopf algebra, except instead of there being a co-multiplication from H to H tensor H, there's a bimodule from H to H tensor H, which plays the role of a co-multiplication. But that bimodule is not equal to H tensor H. And if we consider, situations where fusion multiplicity occurs, these algebras can only detect the anyon type. So there's no extra room in these commutative algebras to know about fusion multiplicity. It kind of means that there's no hope of not having Hopf instead of Hopf-ish when these orange algebras are all commutative ones.
Sorry about Hopf-ish, but what sort of analog of a monoidal structure do you expect on the representation category?
Right, so I think that representations of a Hopf algebra get a monoidal structure from the co-multiplication, and for Hopf-ish, it actually still works. That's annoying, right? Like Hopf-ish works for some reasons, but not having a monoidal structure is not one of them. Good question though. So here's one open question I like to propose. This story is basically the story of how you compute all data in the fusion 2 category, suspension of enriched center of X, where X is your A-enriched fusion category of choice. Now such fusion 2 category is invertible one because enriched center is a UMTC. But it really is that fusion category because there is an equivalence between XX bimodules, which is a fusion 2 category, for those who know, and modules for the center, enriched center of X. And what's the relevance of fusion 2 categories, if I may invoke the cobordism hypothesis again, they're what corresponds to fully extended 3+1D TQFTs. So doing computations in them is relevant if you care about 3+1D TQFT. So we did this in the invertible ones. Can we lift this story, or how much can we lift this story to apply to all fusion 2 categories? What additional inputs are needed to handle the non-invertible, non-trivial center fusion 2 category in a similar Hopf algebroid or Hopf-ish algebroid kind of way? And I think on that note, I'll conclude. Thank you.
So you said your algebra is commutative. Does that relate to the center of the generalized tube algebra?
Yes, so it is perforce the center of the generalized tube algebra, because that is the unique commutative algebra that's Morita equivalent to the generalized tube algebra. And since it classifies the same point defects, it must be Morita equivalent. Now seeing this equivalence is, of course, an interesting and enlightening exercise to go through. That we could go through if you like. Another thing, right, that maybe helps think about this is in the example where we just had the trivial domain walls and x is equal to y, this is just the fusion ring of the center of x, which is of course the center of the tube algebra of x.
Are you saying that you can repeat this computation for cases where I'm doing some SU at level K transaminase theory, or chiral, but theory that you can repeat this kind of computation you just did to the surface and sort of colliding the endpoints?
No, I think that if I understand your question correctly, 2 plus 1D chiral theories and non-chiral, it should all be treated the same by these techniques and work just fine. It's only if it is not even twice extended that what I'm saying here would not really work. That is one of the benefits of working in the anion theory. You don't have to, for example, develop the theory of tube algebras for the enriched fusion categories, which I have done. That was part of my joint work with Penny's, Prudel, Sanford, Green, and so on that I mentioned earlier. But developing that into a C-star Hopf algebroid is another task, and then there are many details to be worked out.
You're assuming semi-simplicity?
That's right. So I baked semi-simplicity into my fusion categories, and also by making the ground field algebraically closed, I baked it into the higher theory even harder, and also there were some pivotality things I didn't mention, which also forced that even more.
Okay. So
So,
have you thought about like what the extension to non-semi-simple would look like, or like would it just break down too quickly?
This is a really good question. I have not thought about it. I'm regrettably very ignorant of non-semi-simple matters. I'm much more into like the unitary world, which again forces you very much into that setting.
This unitary world, as you said, also enforces you these pivotality constraints because your three category has very nice duals always.
Well, I'm not sure I quite say that. So I don't think it's automatic that a unitary fusion category has a pivotal structure. If it does, they can be upgraded to a canonical spherical structure, which is something that Dave Penny's is maybe the guy who loves to talk about the most, I believe, in the world. So if you haven't met him, ask him about it.
Right, so this would be the question then. At the beginning you mentioned that you drew this diagram with the cobordism hypothesis, and this was for the frame setting, right?
Right.
And the three category for the frame setting would not have these duals so nicely picked. So some of these computations would not look so nice where you fold everything like that. But maybe, I don't know, you could still relate it to.
Yeah, that's right. So like I'm using the pivotality super hard. In slightly more physical terms, I might say that I do 3 Wick rotations before I eat breakfast every day, without a single care. So I mean, if you get to a setting where that's more fraught, then probably a lot of the things I'm saying either do not work or have to be proven in completely different ways, at least.
Okay, if there's no more questions, let's thank Peter again.